Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through everything you need to know for the test in a couple of weeks on statistics and probability. Let's start with statistics. So what I've done is just given some random sets of data for two groups, males and females, and we're going to first turn that into a back-to-back stem and leaf. So you've probably seen this a million times. Remember, you have a stem, which is basically the number of tens in the score, and then you have a leaf. For the units, of course, we're going to have a leaf on both sides because this is going to be back-to-back. So on one side, we're going to have males and one side females. So the scores go from 60 to 100. So we have 6, 7, 8, 9, and 10. So all the scores in the 60s go in this row, all in the 70s go in this row, and so on. So let's go and put the scores in there. So let's start with males. So we'll first go through all the scores for males that are in the 60s. So there's only one. So I put an 8 here. So that 8 means 68 because it's in the 6 stem row, the 60s row. So then we'll go through males for 70. So we have 72 and 77. So we put these in order. So it goes lowest and then highest. We'll do the same for the 80s. So we have 84, 83, and 88. Again, we need to put them in order. So it goes 3, 4, 8. And then in the 90s, we have 93, 96, 96, 92. So 92, 3, 6, and 6. So they're in order. So then in the other one, we have 1, 2, 3, 4, 5 scores of 100. So I'm just going to put 5 zeros. So the original data had 15 scores. As you can see, the stem and leaf has 15 scores too. So we know we've done something right. So we go through and we do likewise for the female scores. And so there were only 10 female scores. So that's how you construct stem and leaf plots, in particular a back-to-back stem and leaf. So note that stem and leaf plots are basically histograms on their side. Remember, a histogram is that graph that looks like a column graph, but you always have frequency on the vertical axis. And then the score is on the horizontal axis, and the higher the bar, the higher the number of times the score occurred, the higher the frequency. So let's look at the males. So if we had, 60, 70, 80, 90, all the way up to 100, the male scores would look like this. So there's only 1 in the 60s, there were like 2 in the 70s, 3 in the 80s, 4 in the 90s, and 5 in hundreds. So this is for males. So what you can see is that as the scores increase, the frequency increases also. So what we're seeing is that the scores with the highest frequency are closer to the maximum. The maximum is the score furthest on the right here. So higher scores have a higher frequency here. So we have a name for that kind of distribution. We say that that's negatively skewed. Now, you have to be a bit careful. It sort of goes in the opposite direction than you would think. You'd think positively skewed would be lots of higher scores, but that's not the case. So negatively skewed, it's skewed to the right. There is a higher frequency of high scores. Now, if we were to draw a histogram for females, again, we just need to turn this stem and leaf plot on its side. We'd go sort of in an anti-clockwise direction. So for females, if we put the scores, 60, 70, 80, 90, 100, we would see scores are much lower, but the higher frequency scores are lower. There's 4 in the 60s, 3 in the 70s, 2 in the 80s, and only 1 in the 90s. It's skewed the other way. It looks like sort of like steps, but in the other direction. It's skewed to the left. In this case, the scores with the highest frequency, so those with the highest bars, they are closer to the minimum. And so the opposite, we call that positively skewed. So we would say the distribution of scores for males is negatively skewed and the distribution of scores for females is positively skewed. So this is what a negatively skewed histogram looks like. This is what a positively skewed histogram looks like. Of course, it is possible that a histogram is not skewed in either direction. It could look like this. It could, have bars that are higher, closer to the middle, rather than the minimum or maximum. And in this case, we call that symmetrical. So data is either positively skewed, negatively skewed, or symmetrical. Okay, so now we're just going to have a quick going through of the mean, median, and mode. So I'm actually going to rub out all this stuff, the stem and leaf plot and the skewness. So please pause and copy this down if you need. So let's now go calculate the mean, median, mode, and range for both males and females. So we'll start with the mean. So remember, the mean equals the sum of all the scores divided by how many there are. It's colloquially called the average. So for males, if I add up all the scores, I get 1,349, and I divide by 15 because there are 15 scores. So if you do that, you should get 89.93. Approximately. So that's the mean for males. So for females, if you add them all up, you should get 752. Now we divide by 10 because there are 10 scores. So the mean for females is 75.2. How easy is that? Now let's look at the median. So the median is a little different. It's just the middle. But you have to do it slightly differently depending on whether there are an even or an odd number of scores. So let's look first at males. Well, there's an odd number of scores. That actually means that there will be one middle score. So a trick you can help, a formula you can use is n plus 1 on 2. Remember, n is the number of scores. That does not give you the median, but it tells you which score is the median. So for men, n equals 15. 15 plus 1 divided by 2 is 8. That means the 8th score is the median. Doesn't matter whether you consider it the 8th smallest or 8th largest. So for men, on our stem and leaf plot, we've already got them in order. You have to have them in order to find the median. So we'll go to the 8th score. So 1, 2, 3, 4, 5, 6, 7, 8. The 8th score for men is 93. Okay? How easy is that? Now, for females, there are an even number of scores. There's 10 scores. So if I were to put 10 into this formula, so what I'm going to do is change this to 10. I get 10 plus 1 over 2. Now, that doesn't equal 8 anymore. 10 plus 1 is 11. Divide 2 is 5.5. So that means that the median for females will be halfway between the 5th and the 6th score. When you have an even number of scores, there are always two middle numbers, and you have to find the number that's halfway between them. You take their average. So let's see that for females. So we go 1, 2, 3, 4. This is the 5th score. This is the 6th score. So the median will be halfway between those scores. So those scores aren't 3 and 4, they are 73 and 74. So the median for females is halfway between 73 and 74, which is 73.5. So the mode is usually the easiest to find. It's the most common, the score that occurs the most. So clearly for males, that is 100. 100 occurred 5 times. That's easy as. Now, for females, there were 2 scores that occurred twice, 74 and 67. So they are both the mode. You can have more than one mode. In this case, we have 2 modes, and so we say that females is bimodal, whereas the males, there was only one mode, so we call that unimodal. Okay? Just so you know, if you have no scores repeated, we say that there is no mode. So the range is different to the other 3. Mean, median, mode are measures of central tendency. The point of them is to tell you about the center of the data, what a normal score is. But the range is a measure of spread. It is the highest minus the lowest. Make sure you don't do lowest minus highest, so you'll get a negative number. Range is always a positive number. So for males, the range, the highest score is 100, the lowest score is 68. 100 minus 68 just gives you 32. So that's the range for males. For females, the highest score is 95, lowest is 65, 95 minus 65 is 30. The range doesn't tell you about the center of the data, it tells you about the spread. So another way we can determine skewness is by using the mean and median. So we actually found before that the scores for men were negatively skewed because there was a higher frequency of scores closer to the maximum. So for men, you can see that the mean is 89.93, the median is 93. So when you have the mean less than the median, that implies that the skew is negative. So that supports what we found before, that men's scores here are negatively skewed because the mean is less than the median. Of course, the opposite, if the mean is greater than the median, and we can see that the mean for females was 75.2, the median was 73.5, that means it's positively skewed. Okay, and obviously if the mean and median are close together or equal, then it's symmetrical. But these calculations back up what we found before. Because for men the mean is less than the median, that backs up that it's negatively skewed, and for females the mean is greater than the median, which backs up that it is positively skewed. All right, that's all we really need to know for statistics: how to find mean, median, and mode, how to draw up back-to-back stem and leaf plots, and interpret histograms and distributions for their skewness. Now let's look at probability. So we now turn our attention to probability. So hopefully by now you know that probability is the mathematics of assigning to events, random events, a number between 0 and 1 to indicate how likely they are to occur. If an event has a probability close to 1, it's likely to occur. If an event has a probability close to 0, it's unlikely to occur. So note, whenever I say, what is the probability of blah, 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 you always need to give me a number between 0 and 1. Decimal or fraction doesn't matter. Even a percent's okay. Just has to be a number. So let's look at the question here. In a group of 100 students, we have 60 with blonde hair, 45 with blue eyes, and 25 with neither. We're going to find the probability that if I pick a student at random, the student has blonde hair and blue eyes, and also the probability a student has blonde hair or blue eyes. So here we have a question involving two categories, those with blonde hair and those with blue eyes. So when you have questions involving two categories, Venn diagrams and two-way tables are very useful tools. They essentially provide the information. They just tell you about how many are in each set, and then we use that information for probability calculations. So I'm going to define two sets. I'm going to let set A be the set of students who have blonde hair, and I'm going to let B be the set of students with blue eyes. So I'm going to draw a two-way table and a Venn diagram. You really only need one. Which one you use doesn't matter because they give the same information, but I'm going to go through both so you can pick which one is better for you. So Venn diagrams always look the same. So we've got a box, and inside we have two circles representing two sets. Here, the set of all people with blonde hair and blue eyes. So there are four possibilities. You can be here, 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 or here. You can have blonde hair and blue eyes. You can have both. You can have just blonde hair, just blue eyes, or neither. So those four possibilities correspond to the four numbers that I'm going to put in these boxes in the Venn diagram. So this region in the center here is the overlap. It's in A and B. So we write that in set notation like this, A intersection B. So read that as and or includes everything inside the circles, and that means that it includes both. So when I say A or B like this, so that's or B, that really means A or B or both. It includes both. So that's everything inside circles. So make sure you know those two symbols. So also note that if we have something like A dash, that means not A, or A complement. Okay, so now we've got the notation up and going. Let's go and put in numbers into those boxes. So note 60 plus 45 plus 25. Actually, that's more than 100. If you add that up, you get 130. How is it possible that there are 130 when I said we only had 100 students? Well, that is possible, and the only way it's possible is if I included those extra 30 students, because we've overcounted by 30, if I included them here in the students that have blonde hair, and here, the students that have blue eyes. So I've overcounted by 30, so there must be 30 in the center. However much you've overcounted, that goes in the center. So there are 30 students that have both blonde hair and blue eyes. Now, in the A circle, which is blonde hair, I need to have 60 students. I've already got 30 in the middle there, so I need another 30. So now there are 60 in the A circle here. Similarly, the B circle needs 45. I've already got 30. I need 15 more. So now this circle has 45. And then the number that goes outside is 25. That's the number that have neither. So note these four numbers do add to 100. 30 plus 15 plus 25 does equal 100. So I know I've done something right. So that's the Venn diagram. So let's look at the two-way table now. So a two-way table is a 4x4 table like this. Now, the last row and column is a row for totals. We don't have that in a Venn diagram, but we don't need it. So the two sets, we have A and not A go next to each other, B and not B go next to each other. So these are the four possibilities. The four numbers that go in here, in these four boxes, are the four numbers in the Venn diagram. So this cell here is A and B, students with blonde hair and blue eyes, so we put 30 there. The next cell across to the right, so this one here, are students who are in B but not A, so 15 students who have blue eyes but not blonde hair. And then this cell here, 30 students that have blonde hair but not blue eyes, they're in A but not B. And then neither A nor B, 25 there. So you can fill in the totals if you like. We have 60, 40, 45, 55, these two numbers and these two numbers should add up to 100, and they do, so I know I've done something right. So you can use the Venn diagram or the two-way table to calculate the probability. So, first question was the probability a student has blonde hair and blue eyes. So, blonde hair and blue eyes. So we see that there were 30 of those students out of 100 in total. So 30 over 100, 0.3. Which way you write it doesn't matter too much. So the probability a student has blonde hair or blue eyes. So that means blonde hair, blue eyes, or both. So that's these 30 plus these 30 plus these 30 kids. Here in the two-way table, it's these three numbers. So these 60 people have blonde hair, but we also have to include the 15 that have blue eyes but don't have blonde hair. So 30 plus 30 plus 15 gives you 75. So it's 75 over 100, which is 3/4 or 0.75. That's the probability a student has blonde hair or blue eyes. So let's find what would be the probability of this. So A dash and B dash means not A and not B. What's the probability a student does not have blue eyes and does not have blonde hair? Well, that would just be these people here. They do not have blonde hair and they do not have blue eyes. So that would just be 25 over 100, which is 1/4 or 0.25. So again, Venn diagrams and two-way tables, whichever one you use doesn't matter. They just give information to help you with probability calculations when you have more than one set. All right, the last thing we need to go through is tree diagrams. So tree diagrams are just tools we have to list the possible outcomes of multi-stage events, and then we use them to help us in probability calculations. And I will go through the difference between with and without replacement. So what do we mean by multi-stage events? Just things that occur in stages. So e.g. you might toss 2 or 3 coins. So each tossing of a coin is a new stage. You might roll 3 dice, or you might, draw 2 objects, 2 marbles, 2 cards, whatever. So each of them is a stage, and we use tree diagrams to help us list the outcomes. So let's look at a basic one first. So let's say, for example, we're going to toss 3 coins. I'm going to do a tree diagram to help me list all the outcomes. So going across, you have the first stage, possible outcomes, second stage, possible outcomes, third stage, possible outcomes. Then you list them all in a column, and you can also have a column for the probability. So let's look at it. So tossing 3 coins. So first go, obviously, you can get either heads or tails. And on the second go, even if you got heads first, you can still get heads or tails on the second go. And same if you got tails first up, heads or tails. Then if you toss the coin again, you can get heads or tails. And so on. So you go through and do this, and to find all the outcomes, you just follow all the possible branches. So I'm going to end up with 8 branches here. So the outcomes, I can go head, head, and then head. So that first outcome, I'm just going to write as head, heads, heads. So then, of course, the next one, I could go head again, head, but down to tails. So that outcome would be head, head, tails, and so on. You list all the outcomes that will help you with probability calculations. And as I said, there are 8. So there are 8 outcomes here. Now, I didn't put any probabilities on branches because they are all equally likely. There are 8 outcomes, all of them as equally likely as the others. So each of them has a probability of occurring of 1 out of 8. So now that I've drawn the tree diagram, I could answer probability questions pretty simply. So if I toss 3 coins, what would be the probability that I get 2 heads? So all I need to do is go and look at the outcomes where there are 2 heads. So this one has 2 heads, this one has 2 heads, and this one has 2 heads. So there are 8 outcomes in total. There are 3 ways that I can get 2 heads. So remember, probability of an event is just the number of ways the event can occur over the total number of outcomes. So there are 3 ways I can get 2 heads. Head, head, tails is 1. Head, tail, heads is 2. Tail, head, heads is 3. And there are 8 possible outcomes. So what is the probability that I get, let's say, at least 1 tail? Well, that's pretty simple as well. I just go through and calculate the ones that have at least 1 tail. So this one has at least 1. At least 1 includes 1 as well. So I include this one as well. This one does. In fact, all of them do have at least 1 tail except the top one. So there are 7 ways that I can get this, have this happen, out of 8 in total. So what is the probability that I do not get heads in any of them? Okay, well, that's pretty simple. You just go through, find which ones do not have heads. And it's only this one down here. There's only one way that I can toss the 3 coins and not get any heads. 1 out of 8. How easy is that? So this is an example of with replacement. Now, I know you're probably thinking, well, we don't actually replace anything. Well, physically you don't. But if you get a head on the first go, the head is replaced. You can get heads on the second go, and there's the same chance of getting heads on the first go as the second go. That's why it's with replacement. Now we're going to look at one that is without replacement. So please pause and copy down if you need. So let's now look at this example. Say I have a bag that has 1 red, 1 grey, and 1 pink marble, and I'm going to pick 2 without replacement. So I'm going to pick 1, I'm not going to put it back, then I'm going to pick a second one. So let's look at the possibilities here. So again, we have 2 stages. That's why we're using a tree diagram. We're picking a marble, picking a second marble, and that's why it's a multi-stage event. So first go, I could get the red, I could get the grey or the pink, no problems there. But if I get red first go, because it's not being replaced, I can only get grey or pink the second go. And if I pick grey first, I can only get red or pink the second go, and so on. So this is what my tree diagram looks like. It's not like the last example, which is with replacement, because if I got a heads the first go, I could get heads the second go. Here, I can't get the same thing both goes. So the outcomes, we have red and grey, red, pink, and so on. So there are 6 possible outcomes. Again, they are all equally likely. So each of these has probability of occurring of 1/6. So that helps us answer probability questions. So if I pick the marbles, as I said, I pick one, don't replace it, then pick another one at random. So what would be the probability that I do not pick a red marble? So all we do is go through and we look which ones don't have red. This one and this one. So there's 2 ways to do it out of 6 in total. So there's a 1/3 chance that I don't pick a red marble. What's the probability that I pick grey first go and then pink the second go? So I just go find how many have grey the first go and then pink the second go, just that one. So the probability of that happening is just 1 out of 6. How easy is that? It makes the probability calculations a lot simpler. So I gave you one example of with replacement and one without replacement. These were examples where all outcomes are equally likely. So the last thing we're going to do is look at where the outcomes are not equally likely, and you need to put probabilities on the branches. Hearts. So we're going to look at this example here. So I'm going to draw 2 cards from a normal deck of 52, and I'm going to find the probability that only one of the cards I pick is a heart, the other is a different suit, and I'm going to find the probability when the experiment is both with and without replacement. So I'm going to use tree diagrams. This is a multi-stage event because I'm drawing 2 cards. So let's start off by looking at with replacement. So I'm going to draw a tree diagram. So of course there are 2 stages, first draw and second draw. So I'm not going to go and list on the first draw all 4 suits because I'm only interested in whether the card was a heart or not a heart. If I write hearts, diamonds, clubs and spades, there's just more branches. So that's what I can get on the first go. Second go, of course, I can get heart or not a heart, regardless of what I got the first go. Okay, so there are 4 possible outcomes here. So we have hearts and so on. The thing is though, they are not equally likely to occur. So you can't say that the probability of, say, getting heart and then another heart, this one here is 1 out of 4. They're not equally likely because, of course, you're more likely to not get a heart than you are to get a heart. So what I have to do here is write probabilities. So the probability of getting a heart is 1/4 and of not getting a heart is 3/4. Now, because this is with replacement, when I take the first card, I put it back and then take a second card. So the probability of getting a heart on the second go is still the same because I would have put the first heart back. So it's 1/4 of getting a heart each time and 3/4 of not getting a heart. So how I calculate the probabilities is I multiply them. So the probability of getting heart and then a heart is 1/4 times 1/4, which is 1 out of 16. The probability of getting a hearts and then hearts the first go and then not a hearts is 1/4 times 3/4. So that would be 3 over 16. And the next one will be 3 over 16. The last one, 3/4 times 3/4 is 9 over 16. So I have a 1 in 16 chance of getting both hearts. I have a 9 in 16 chance of getting no hearts. So the probability I get 1 and only 1 heart. So I could get this or this. I could get hearts the first go but not the second go, or I could get hearts only on the second go. So what is the probability that that only 1 card is hearts? So that is 3 over 16 plus 3 over 16. You add those two possibilities together. And that just gives you 6 over 16 or 3 over 8. So you have a 3 over 8 or 0.375 probability of picking only one card that's hearts. So I'm going to redo this tree diagram now, but now we're going to do it without replacement. So that is when I take a card and I don't put it back before taking a second card. So that will just change the probabilities only slightly. I don't need to change the whole tree diagram because I still have the same outcomes. I can still get a heart first go and second go, right? Because the first go, there are 4 hearts to choose from. If I get a heart, there are still 3 more to choose from. So the only thing that will actually change are these probabilities here. So I'm just going to rub them out. So now we're going to go and do without replacement. So what will happen then, that means these will change as well. That's the only thing difference. So the first go, there's still a 1 in 4 chance of getting a heart. But if I take out a heart from the deck, I started with 13 hearts. There are now only 12 hearts left and 51 cards in the deck. So I'll just rub that out, write that again. So you start off with 13 hearts in the deck. If you pick one, there are 12 left, but there are only 51 cards left because you've taken one out. So then the probability you don't get a hearts, well, there were 39 cards that were not hearts. There are still 39 cards not heart out of 51 in total. So this number here and this number here should add up to 1, which they do. So let's say on the second go, so it is supposed to be not hearts. So there's still a 3/4 chance that you don't get hearts on the first go. If you don't get hearts on the first go, when it comes to the second go, there are still 13 hearts left out of 51 cards in total. So that will be 13 over 51. If you don't get hearts on the first go, there are going to be 38 cards left that are not hearts out of 51. So again, how we figure out the probabilities is multiplying them. So we go 1/4 times 12 over 51, and that actually gives us 1 over 17. So before, the probability that you got both hearts was 1 over 16. It's now changed slightly. It's now 1 over 17 if you don't replace the hearts when you get it first go. And we do the same for the others. We do 1/4 times 39 over 51. So that gives you 39 over 204. The next one is 3 over 4 times 13 over 51, same number, 39 over 204. And then the last one will be 3 times 38 over 4 times 51, which will give you 114 over 204. So just so you note, 1 over 17 is 12 over 204. If you add up all these, they add to 1, which means we've done something right. So what will be the probability I only get one heart? So I can get it this way or this way, so I just add those two up. It will be 39 over 204 plus 39 over 204, which will be 39 over 102. So the probability has ever so slightly changed. So when I did replace the card, the probability of getting only one hearts was 3 over 8, which is about 0.75. If I don't replace the hearts, the probability of getting hearts has gone up slightly. It's now gone up to about 0.382, whereas it was 0.375. We see that the probability is only slightly changed when we change the experiment from with replacement to without replacement. All right, I'm very sorry about the long video. Please come to tutoring, ask any questions if you need. Best of luck studying. This has been the luckiest maths teacher in the world. Have a great day.